Okay, so we'll revise the concepts of Fourier series and Fourier transform. So the first concept is periodic signal can be written as a linear combination of sinusoids, and if sinusoids, these have the frequencies integral multiple of the fundamental frequency, that is k omega naught, where omega naught is 2 pi by t being the fundamental time period. Now, using a definition of inner product as the inner product defined as 1 by t time integral of first into the complex conjugate of the second, we obtain we observe that if we take the inner product of two sinusoids of different frequencies, integral multiple of the fundamental frequencies, the inner product is 0 for those being not being equal and equal to 1 for those being equal, that is k equal to n. So hence we have obtained a way to get the coefficients of each exponent, and hence we can express the a periodic signal in terms of uh, sinusoids of integral multiples which have basis as e to the power j k omega naught t. Now, so to obtain ak, we'll take the inner product of LHS and RHS, and since it all the terms except k equal to n, those vanish, and we get an. So an is inner product of function with a general ak is the inner product of function and e to the power j k omega naught t, and by definition of inner product it can be written as 1 by t integral f of t e to the power minus j k omega naught t dt. Now if we plot ak versus k or ak versus k omega naught, that is known as frequency domain representation, and the relative magnitudes of ak would suggest which sinusoids uh, has will dictate the overall formation. Now extending this to aperiodic signal, so an aperiodic signal can be thought of as a periodic signal with fundamental time period tending to infinity. That is to say that a aperiodic signal would repeat itself after infinite time. So uh, so since the fundamental time period tends to infinity, the fundamental frequency in radian per second would tend to 0, and now to write the decomposition into sinusoids, we need to apply the limit tending to infinity from the expression of ak. We substitute here and replace t by 1 by t by omega naught by 2 pi. Now we observe that omega naught tends to 0 as t tends to infinity, and the summation is from k equal to minus infinity to infinity, and k omega naught t into omega naught. So since omega naught tends to infinity, this can be thought of as the d omega, that is a differential omega, and k omega naught tends takes all the values of frequencies from minus infinity to infinity. Hence considering this the first integral, that is the circled region, as a separate function capital F of omega, uh, summation e to the power j k omega naught t d omega. Now this can be thought of as an integral over every possible omega from minus infinity to infinity d omega. Hence now our periodic function, aperiodic function, has been decomposed into uh, an integration of sinusoids. So the important difference is here we had uh, discrete frequencies, integral multiple of fundamental frequencies, but here we'll have entire range of omega from minus infinity to infinity, and the circled uh, term here is represents the uh, coefficient of each sinusoid, and that is called the Fourier transform of f of t, since it represents the magnitude of each sinusoid. Hence it in some sense is the uh, frequency domain representation. And the representation of uh, the aperiodic signal in terms of sinusoids is called the inverse Fourier transform, since it is the transformation of from frequency domain to time domain. Now similar to the periodic case, here we had ak, here we have f of omega, which is the scaling of e to the power j omega t in the decomposition of f of t. Okay, thank you.